Here is a short note about transport coefficients or thermal transport coefficients, which can be calculated in simulations. The general form of transport is J equals minus L multiplied by the gradient of some quantity x. So J is the response of a system to a perturbation in the system, and these are linked via the transport coefficient. For example, if you apply a concentration gradient across, let's say, a cell membrane, then this is linked to the flux across the membrane by the diffusion coefficient. So J is the diffusion flux. It has units of moles per meter square per second. T is the diffusion coefficient. This could be meter square per second. And this here is the concentration gradient. So if the transport coefficient is D, then you are transporting material. If the transport coefficient is K, which is the thermal conductivity, then you are transporting heat. So if you apply a temperature gradient across a rod, you're transporting heat, and this will be related to the thermal conductivity. If the transport coefficient is the shear viscosity, then you are transporting momentum. So the question is, how do we calculate these transport coefficient from simulations? Now, in our simulations, we do not have a concentration gradient or a temperature gradient or a momentum gradient, but we can still calculate these transport coefficients from equilibrium simulations by using what is called the fluctuation dissipation theorem in statistical mechanics, which essentially relates the linear response of a non-equilibrium system. So this could be a concentration gradient applied across a membrane to some fluctuations of an equilibrium system. So this is also called linear response theory. So you do not need to go further into the details of these, but I'll give you a simple example. So for example, the diffusion coefficient in 3 dimensions can be calculated from what is called the Einstein relationship. For very long times, in the limit of very long times, the diffusion coefficient can be calculated from this equation. Here T is time. The mean is taken over all particles of the system, and RIT minus RI0. So this is the fluctuation of the position of the particle from its initial position. So this can be calculated from an equilibrium simulation, just like the ones that you are running, and we can still get out the diffusion coefficients. Now this equation is for diffusion in 3 dimensions. If you had diffusion in 2 dimensions, this 6 would be simply replaced by 4. You can read about this in Leach, which is your textbook. You can also calculate these diffusion coefficients from autocorrelation functions. So the D can also be calculated as 1 by 3. This is a 3-dimensional diffusion coefficient, and you integrate this equation to infinity, and this would be the velocity autocorrelation function integrated for a very long time. Right? So the whole message from this is that you can obtain transport coefficients such as the diffusion coefficient, the thermal conductivity, the shear viscosity, even the dielectric permittivity from equilibrium simulations using relationships similar to this. You can also calculate a viscosity.